record. I don't know if the recording in progress robotic voice is audible to you all, but I always find it kind of funny because I don't expect the robot voice to come out. Anyhow, today we're going to have the first of two labs that are focused on another part of the rock cycle, and that's what happens when rocks are broken down and how the broken down remnants of those rocks are converted into new rocks, known as sedimentary rocks, over geologic time. So the first lab, the lab that we're doing today, focuses more on the processes of weathering, or the breakdown of the rocks, and then what happens to the minerals in those rocks, as well as what minerals make up sedimentary rocks in general. And next week's lab will focus more on different types of sedimentary rocks themselves. By the way, anyone can tell me where this is, what this location in this picture is?
Is it Utah?
Very good guess. Utah does have some places with features like this. I think you're thinking of kind of Monument Valley with the big stacks. So that's a very good guess. Another really interesting sedimentary place, but this is actually in California. This is kind of in inland California. Other guesses?
San Francisco?
Very far from San Francisco, indeed. San Francisco is more on the coast. This is in the deserts inland. This is Mono Lake. This is actually a picture of some really cool features related to sedimentation that you see at Mono Lake. These are towers of tufa, or a type of limestone that form when the water evaporates, and they actually leave a mineral that you've seen before, calcite, behind in these forms. And this is one really cool example of how interesting formations form when stuff dissolved in the water ends up being left behind in a place where the lake dries out frequently, or where the lake changes level frequently. So if you do ever get a chance to go to Mono Lake, it's very cool. These features are quite impressive and very spooky. But they are, I bring them up because sediments, we often think, if you hear sediment, like if you think about sand in a dam, or you think about mud, and those are definitely types of sediment, but it turns out that a very important group of sediments are actually the products of chemical breakdown of rocks. And those chemical ions that end up being broken down from the rocks actually concentrate elsewhere later and end up concentrating elsewhere. Oh dear, Heather is having a hard time entering this. I don't know quite what's going on there. Does it? Okay. I apologize if I seem distracted through this presentation. I'm just going to do what I can to make sure Heather can get in the presentation. So this lab is the only thing that will be due next week. There is not a quiz due next week. There will be a quiz covering both this lab and lab 7, which is the second part of the lab, that will be due on April 5th. And I also, again, wanted to mention that there's a number of geology seminars being hosted by Cal State Northridge, and there's one happening next Tuesday at 4:30 p.m., so it's a bit after this lab period ends. And it is a chance to get extra credit. I'd said 2 points previously is what you'll get from doing a write-up based on one of these presentations, but I am actually going to make it 3 points just because I think it's a bit of a time commitment to show up to one of these, and I think that's more fair. And basically, if you write about what you learn at one of these seminars, I can add those 3 points to any quiz or lab that you feel you wish you had done better on. So that's, if you end up attending one of these, you can ask me what to write about. It's pretty open-ended, but you can also then tell me what what assignment you want to add the points to. So let's talk about sediments a bit. What is sediment? Sediment is a general term for unconsolidated particles. And when I say unconsolidated, I mean they haven't become a rock yet. They haven't been solidified into rock form. And what sediments can actually be chemically can be almost anything. But normally for geology, we break sediments into two broad categories. And those are clastic sediments and chemical sediments. And clastic sediments are what we think of as, well, classic sediments. What I think most of us think of when we think of sediment: sand, pebbles, mud, and clay. Here's a question: do boulders count as clastic sediments, do you think? If clastic sediments are fragments of any rock, and you are indeed correct, Viviana. Yes, boulders are very large clastic sediments. Boulders form when rocks get broken into large pieces, and then when they don't further get broken down into small pieces. And so where I live in Santa Barbara, where I live in Santa Barbara, there were a number of big mudslides a couple years ago, and a lot of the damage came from boulders, and the boulders were actually carried by really fast-moving water. Something we'll talk more about in the next lab is that since sediments are carried by water so much of the time, the speed of the water actually has a lot to do with how big a piece of rock the water can carry. Let me. I apologize. I am going to briefly stop the share and see if I can do anything to help Heather out, because she seems to be having trouble getting in here. Participants invite. Sorry. Okay. I apologize for doing this. I just going to send her an email really quickly. In the meantime, does anyone have questions while I shoot an email to her, just to see if this gives her a better chance of getting into the meeting, because I don't know why it's locking people out. Okay, so let's go back to screen share mode. I apologize for the interruption. This is not the first time that Zoom has misbehaved. Okay then. So and what about chemical sedimentary rocks? And it's a bit of a harder concept sometimes, but one thing to keep in mind right away is that sediments that are clastic and chemical fundamentally come from the same processes. Chemical sedimentary rocks consist of the salts and the other compounds that precipitate or fall out of the water. If any of you have taken a chemistry class where you were putting different compounds in water, sometimes what'll happen is if you put too much of it, everything will fall out of the water at once, and that's precipitation. And that's actually something that happens in geology too. And it often happens when the water that was there before evaporates or turns into gas form and leaves behind whatever was in the liquid water before. And so you'll have manganese, like these manganese nodules here, or calcium carbonate, what makes up calcite, or rock salt kind of sprinkle out. And fundamentally, this all comes from the weathering, breakdown, and transportation of the pieces coming from rocks. And they accumulate in basins. Basins are going to be a place where the sediments are accumulating or building up as opposed to being carried away. So the ocean, lakes, and then also inland basins, like when you have sediments just accumulating in a valley, those are all places where sediment builds up. So how does a sediment become a sedimentary rock? And to a big extent, it's because it gets buried. If we start on this diagram with an outcrop, which is just a generic term for there's rock at the surface of the earth, the rock fragments that make up sediments, as well as the chemical ions that make up chemical sediments, originally come from that outcrop. And in this case, I picked El Capitan because that's a pretty prominent feature that in the Sierra Nevada, and it also was Heather able to get in? Oh, Heather got, okay, Heather, you're here, good. I apologize, I don't know what happened. I don't know what was up with Zoom. I really apologize for that. But this will be recorded so you can watch the first bit later if you need to. You didn't miss that much. But anyway, a lot of the rocks that we have exposed at Earth's surface on land are granites, and those granites get broken down. And an important thing to consider is that any type of rock can be broken down to become sediment, but a lot of the time, the source is igneous rocks, like the granites we've been studying. And what unites all three of these rocks, igneous, sedimentary, and metamorphic, is that they can become outcrops that will be eroded. And something you'll see here is the term uplift, showing you that these rocks have been taken above the Earth's surface. Uplift is actually, to a big extent, what causes erosion, because when rocks get put up at the Earth's surface, they become exposed to water, they become exposed to wind, or glaciers if you're in a place like Antarctica or Greenland. And then another factor is that as they become higher, they become more susceptible to the force of gravity. Gravity actually plays a role in helping to break down rocks. And the rocks will break down into boulders, sand, and mud. And those are all terms for clastics or rock fragments. And you'll also have ions breaking off of them. And I chose this beach because it's in Santa Barbara, and it's El Capitan State Beach, which is I don't think not much of the sediment from here necessarily ends up here, but I think it's kind of fitting in that what starts as solid rock ends up being broken down and ends up actually being the sand you find on beaches. And that's sediment that's being deposited in a basin, that being the ocean. And what happens to the sediment? It gets buried, compacted, and cemented. Now, what about the river in this last picture? What's the river doing? And the river is not only physically what's carving this canyon. This is from Utah, actually. This particular picture here is from a park called Goosenecks of the San Juan River in southeastern Utah. But the river is actually what's carrying the sediment. It's not only physically breaking the rock down, it's chemically breaking the rock down and carrying both the broken off pieces of rock and the chemicals that have been chemically eroded from the rock away and eventually into a basin, eventually into the ocean. Not every river carries sediment to the ocean, but in general, that's what happens. So questions so far? Now, I have a bit of a quick sort of stop motion animation kind of showing what happens over the course of this. And I'll walk you through these steps. I wanted to give you an overview of the process of how sedimentary rocks form. And this series of slides, I think, does a nice job of showing you how we go from weathered rocks to sediments being deposited in basins and then forming sedimentary rocks. And the basins are going to be lakes, oceans, or sometimes in what's known as an alluvial fan, which is actually something you see pretty frequently in the area where you all live, because you're in a dry area where you don't have many large rivers taking the sediment out to land. So a lot of the time, the sediment just ends up being deposited in valleys and staying there. And hopefully this gives you a sense that all rocks can be eroded, because you have both these plutons, which are made of granite like we've been studying, and then you also have volcanic rocks or extrusive igneous rocks overlying the intrusive igneous rocks. Both of those can be eroded into sediments. And you can also have metamorphic rocks, which are represented by these squiggly lines here. And we haven't really covered metamorphic rocks yet, but they're rocks that change texture and chemistry substantially under intense heat and pressure. And we'll get to those in lab in a couple of weeks, but those can erode to form sedimentary rocks. And indeed, previously formed sedimentary rocks, like they're often shown as these layers here because, as we'll talk about, sediments form layers that pile up on each other over time. But these sedimentary rocks can also break down into more rock, into sediments. They can break down into sediments that will subsequently form different sedimentary rocks. And one thing we'll cover a bit in this lab is how to identify what's known as the provenance of sediments. And provenance in a geologic sense means where the sediments came from, what type of rock they came from, whether it's basalt or granite or a metamorphic rock or another sedimentary rock. And we often figure that out by looking at the minerals. So erosion, so weathering is the breaking down of rocks. You've probably come across the term erosion before, and people often use erosion and weathering interchangeably. But erosion is specifically the removal of the weathered material from its initial location. And so glaciers or liquid water or air will carry the broken down pieces of rock, as well as the chemical sediments, in the case of the liquid water, away from their source. And then they'll be transported downhill. And it's not a coincidence that the basins are low points. The sediments get carried by the force of gravity because the water and the glaciers also, and to some extent the wind can kind of blow stuff in all directions, but when thinking about water or glaciers, they flow downhill, carrying the sediments with them to basins. And in Santa Barbara, where I am, the transportation doesn't take that long because I live really close to, on a little, a lot of coastal California is kind of just this little strip. There's the mountains just a few miles inland, and then whatever sediments break down from those mountains don't have very far to travel. But if you think about a place like the Mississippi River, like a lot of the eastern United States, the sediments can be carried a really long distance along really, really long rivers. And one thing we can do is we can actually use the textures of the sediments as well as the rocks formed from them and their mineralogy to figure out how long they've traveled. Because sediments that have traveled a long way are going to look somewhat different from sediments that have only traveled a little bit. And this is an alluvial fan, what I was talking about earlier. This is from Death Valley, but you do see them closer to where you are in the Antelope Valley as well. And it's because Death Valley and the Antelope Valley are both places where a lot of the sediment doesn't make it to the ocean. Because California is pretty dry, simply put. There isn't enough water to carry this sediment away from the mountain, and so the sediment just kind of forms this pile here at the base of the mountain, this triangular fan-shaped pile of sediment. And notice how it looks kind of like the fan shown in this diagram of the ocean. This forms where further out in the ocean, the water is a lot calmer, and whatever has been carried out first by rivers and then transported by waves closer to the shore, farther away from the shore where it's calmer, the sediment just falls out of the water because the water is calmer. And that's a good example of how you have two separate types of basins, places where sediments are accumulating. Again, the ocean is usually where sediment ends up, but some of it does kind of get stuck on land. And deposition is when the ions or rock fragments reach their final settling place before being turned into rock. And really, sediment is any material that is deposited, both rock fragments, whatever rocks those might be from, and also the chemical ions broken off from the rocks by chemical processes. And of course, they don't just sit there, they get buried. Sediments get covered up by more sediments, and that's why sedimentary rocks are layered, because they're made of the accumulation of the same processes, dropping sediment on top of previously deposited sediment over geologic time. And layers upon layers of these sediments can be deposited over the course of days or weeks or decades or even millions of years. And then what actually turns it into a sedimentary rock? The process of lithification. And lithification is actually a general term for when anything is turned to rock, but it's often used in the context of sedimentary rocks when the sediments become hardened by the pressure of the younger sediments on top of them. The sediments that are buried further down get compacted by the pressure of the overlying sediments. They get cemented together and they form into a solid rock. And we'll talk about in a future lab how when the pressure gets high enough, and actually when they get buried enough that they start to be affected by the interior heat of the earth, they undergo extreme changes in texture and mineralogy that turn them into metamorphic rocks. Sedimentary rocks form at the less extreme end of that. So that's the last of these slides on the process of sedimentation. Does anybody have questions about any of this before I move on? Okay, cool, then I'll keep my eyes on the chat and feel free to chime in if anything is confusing. So let's get into some terms. Erosion is actually a term that encompasses the whole process, but it's often understood as just physically breaking down the rock. And weathering is the term for the breaking down part itself. There's both chemical weathering, which is destroying a rock via chemical reactions, and physical weathering, which is physically breaking it down. And the two processes actually usually happen simultaneously. One will often dominate, but it's very rare, at least in cases where the main agent is liquid water, that you'll have chemical erosion with no physical weathering whatsoever. Maki, get off the keyboard. My cat wants to learn about geology even though she doesn't understand the terms. Go back to your bed, baby girl. She's blocking my notes. And why do the two happen simultaneously? It's because the same agent, often water, performs both actions. Water actually can physically break down rocks as well as cause chemical reactions with the minerals in the rock that cause them to break down even further. Maki, get off the keyboard. And some things to consider are that in different areas or with different types of rocks, rates of weathering are going to be different. We can probably guess that if you're in an area that's hotter and wetter, chemical weathering is going to be faster. And in general, in a place like a desert, in fact, you don't get a lot of chemical weathering. You'll get some surface staining. You'll get some what we call oxidation or rusting of the surfaces of the rocks. But if there's not a lot of rain, not much chemical weathering will occur. And a consequence of that actually is that dry areas like deserts don't form much in the way of soil, because the presence of more water allows faster soil formation, in part because you have more biological activity. And one thing I'll talk about is that biological activity from plants and microorganisms actually speeds up chemical weathering. Soil is a product of both physical and chemical weathering, actually largely from plants. Another thing is the surface area. The more surface area of a rock that is exposed, the faster it'll break down. So a large boulder will not weather very quickly necessarily, but if that boulder gets broken into multiple pieces, like in this example here, you'll have a bunch of little rocks and more of their surface area is exposed. The inside of this boulder is in a way protected from weathering, but if that boulder gets broken down into a number of pieces that together are the same volume, but they now have their sides exposed, there is a bunch of little blocks, there's more surface that is exposed to the air or water that the air or water can attack and break down both physically and chemically. And then Bowen's series comes back into play, because it turns out some minerals weather faster than others. Something I'll talk about is that temperatures that form, minerals that form at really high temperatures, like olivine, tend to break down pretty quickly at Earth's surface. They tend to be rather unstable at lower temperatures, and Earth's surface is obviously at a much lower temperature than the hot temperatures underground at which those minerals formed. So again, physical weathering is a bit more intuitive. Technically, if you remember that video that I showed you to indicate calcite cleavage, where that person just used a little rock hammer to smash the crystal open and show its cleavage, that is a type of physical weathering. And if geologists are out in the field using their rock hammers to smash rocks open, that is a very small scale and rather ineffective form of physical weathering. And physical weathering usually doesn't involve large impact. It doesn't usually involve that. It involves the water or air or glaciers gradually removing little bits of rock over time, like how glaciers will kind of scrape the rock underneath them, or how water going past rocks will over time cause little bits of the rock to fall off. And in pure physical weathering, the smaller pieces of rock are the same chemical composition and have the same minerals as the starting rock. If you only have physical weathering, it's just breaking the rock into smaller pieces without actually changing its chemistry. And chemical weathering means that in the case of if liquid water is involved, the water or something dissolved in the water is chemically reacting with atoms in the minerals so that they become dissociated from the minerals and dissolved in the water, like in this example here. It's a little bit hard to see here, but you have the even surface of a mineral, and that mineral starts to show little pock marks because the water is actually causing atoms that were previously part of the mineral's chemical structure to separate from that. And so you have what are known as, and so you have a leftover rock that is now chemically different, and then you have ions in the water. And so the reason that this happens is because water is polar. Water is a single oxygen atom bonded to two hydrogen atoms, and if you think about atoms having positive and negative charge, the oxygen atom tends to develop a slightly negative charge, whereas the two hydrogen atoms have more of a positive charge, and that has to do with their atomic structure. Oxygen, simply put, likes electrons, to anthropomorphize them a little bit, and so electrons are the part of an atom that makes them negative, and so the oxygen atom will tend to be more negative, and that'll leave the hydrogen atoms more positive. So a water molecule is technically neutral, but it has one end that is sort of partially positive and one end that is partially negative. And what that means water can do is it can interact with other atoms to form new ions. And it's kind of cool because water can kind of function as either the positive attractor or the negative attractor, depending on what the other atom is like. This is a really simple example of actually a mineral that very easily is susceptible to chemical weathering. And the in this case, you have positive sodium ions that get attracted to the negative end of water. You can see the little purple sodium ions, which have a positive charge, get attached to the oxygen. And then the chloride ions, which are negative, are more attracted to the partially positive hydrogen atoms on the water. And so that allows water to break up substances like this. And most rocks don't chemically weather this easily because rock salt just is simply nothing but sodium and chloride put together. It has a pretty weak structure, and water just kind of dissolves it. But most other minerals, this doesn't necessarily happen to the extent where the whole thing gets dissolved, but enough ions can get taken off that that you have a noticeable amount of those ions ending up in the water. Now, the interesting thing about rock salt is we'll find out it actually forms often as an evaporite, or a deposit that forms when you have ions dissolved in the water, and then the water gets evaporated and this gets left behind. So if the sodium didn't originally come from rock salt, what's a possible mineral where the sodium could have come from before it ended up in the water? Are there any minerals that you've seen that have sodium in them? Or Na? Halite does have sodium in it. I'm looking for a mineral other than rock salt, because this is halite or rock salt, and I'm looking for another mineral that the sodium could have been broken down from before it ended up as rock salt. So I didn't really have you linger on chemical formula, but it's actually feldspars. A lot of the sodium actually comes from feldspars originally. And Kat really wants to be involved today. And the breakdown of feldspars ends up putting sodium in the water, and that water is either going to end up in the ocean, or in some cases, it's going to end up in places like Badwater Basin, Death Valley. If any of you have been lucky enough to go to this part of Death Valley, it's known as Badwater because you have a couple little stagnant pools of water, and then you have just all this salt lying around. And all that salt is from dissolved sodium and chloride ions that were in the water, the water was washed down to the valley floor during storms and flash floods. And when the water dries up, the salt gets left behind and doesn't really go anywhere. It just, since it's so dry and since the water doesn't really have anywhere to go. In this case, because Death Valley is so sunken down, Death Valley is below sea level, so it doesn't really make sense that the water is going to flow outward towards the ocean, because Death Valley is actually lower than the ocean. But the salt gets dried up and left behind, the water gets dried up and the salt, which can't really go with the evaporated portion, gets left behind. And this is why you see salt in deserts, because the water can't go anywhere. Now, if you have more continuous water flow, those ions get carried to the ocean instead. And I'll talk about the consequence of that on the next slide, but you might be guessing where that's going. And I also do want to introduce the term evaporite, which I don't know if that's something you've gone over in lecture, but it's a useful category because a number of the important sedimentary rock forming minerals are evaporites. They're minerals that form when the water with dissolved ions in it evaporates and leaves behind minerals that form from those dissolved ions, like halite or rock salt. And so what you get if you have more continuous water flow is that actually these ions get carried to the ocean. And both plagioclase and orthoclase feldspar, the two different types of feldspar you looked at, have sodium in them. And feldspars make up a very large percentage of granites and other rocks that are found on land, found on the continental crust. And when those granites get chemically weathered, the sodium gets transported by the water, and that sodium actually ends up in the ocean. So it turns out that the reason the oceans are salty is because that's where sediments are ending up, and that's where all of the vast majority of the sodium being eroded from the feldspar and these granites is ending up, which I think is really cool. And this is because the amount of sodium in the oceans has been pretty consistent over recent geologic time. When continental crust began to form more, it stabilized. The amount of sodium in the oceans sort of came to equilibrium as erosion came into play. And lakes are generally not going to be as salty because you usually have water flowing out of them. You have water taking some of the sodium out of them and in the form of outflow rivers. But you often get salty lakes in places like Death Valley where there's no place for the water to flow out of. So in general, where the water ends up, whether it's the ocean or whether it's a basin like an inland basin like Death Valley, the water is going to be salty. So any questions about this so far? So you want to think about the fact that different minerals break down to form different ions. And I didn't really linger much on the chemical composition of minerals, except to remind you that the more mafic minerals are going to have much more in the way of magnesium and iron ions. And indeed, when you get minerals like olivine or pyroxenes breaking down, that produces iron and magnesium ions. Whereas something like plagioclase feldspar, which has both calcium and sodium in it, is going to produce calcium ions and sodium ions. And calcium is important because another really prominent mineral that we find in sedimentary rocks, calcite, which is actually the mineral that was making up those stacks that I showed you on the first slides, the ones from Mono Lake. That calcium also comes from the weathering of feldspars. And likewise, there's potassium in the ocean, and that comes from weathering of alkali or orthoclase feldspars, the pink ones that you've been looking at over the past couple of weeks. And something really interesting is that quartz doesn't really readily weather at all. Silica, quartz is just pure silica, and in fact, quartz, when forming from magma, it's the last to cool, and quartz kind of forms from whatever silica doesn't go into these other minerals. Quartz is kind of, in some way, leftover junk mineral. It's like you use a bunch of you use an ingredient up for a bunch of recipes, like you have chicken broth, and you put chicken broth in a different bunch of soups, and then when you don't have any more soup to make, you just use the broth for when you're sick or something. I don't know if that's the best example, but quartz is kind of the leftover silica. And SiO2 by itself is very immobile in water. Water does a very poor job of chemically interacting with silica and breaking it down. And so quartz doesn't readily chemically weather, excuse me. It breaks down physically, although it's actually pretty hard to break quartz down physically because it's such a hard mineral. And often in sedimentary settings, we actually find that quartz is kind of the last mineral left. It'll often be one of the last minerals left in the rock itself when the rock is being broken down. And then if you have sediment that's being transported by water, the water will cause all sorts of chemical reactions with the pieces being transported by it. If there's pieces of basalt or peridotite that have olivine in them, the olivine will react with the water. Feldspars will react with the water, but the quartz won't. And that's actually one big reason why in places like the east coast of the United States, if any of you have ever been to the Gulf Coast, I actually haven't, but I've seen pictures of it, and it's really interesting to me just how much the beach sands there are different from California beaches. Because California beaches, the rivers carrying sediment there don't actually travel that far from either the coastal mountains or from the Sierras. But the water, the sediment that's ending up on the beaches on the Gulf Coast has been carried by the Mississippi River, which has been going for hundreds of miles. And a lot of that sand is just quartz because the quartz is all that's left. And so the fact is that the mafic minerals break down more easily. The mafic minerals form at really high temperatures, and you need really high temperatures to melt a rock to the point where you'll produce a melt that can subsequently form mafic minerals. So rocks like basalts or gabbros, which are like gabbros are like granites, but they're mafic. Gabbros are the coarse-grained equivalents of basalt. And also ocean peridotites, the mantle is actually made of this rock. The mantle is almost entirely made of olivine. And if those get exposed at Earth's surface, they will break down very quickly because those minerals at the top of Bowen's reaction series are simply not very stable at room temperature, at Earth's surface temperatures. And so those rocks don't last very long. And it's one reason we actually don't have, aside from the fact that it's hard to access the ocean crust, there are some times when ocean crust does get exposed at Earth's surface for whatever reason. And those exposures don't tend to last very long before they're eroded. So we don't have a lot of older examples of them. Whereas quartz just simply doesn't chemically weather at all. And this is a good close-up as to what quartz sand looks like. This is actually the sand that they use to make glass, because they look for sand that, or they either look for or they refine sand to the point where the other minerals just aren't in it. And the silica, again, just isn't very fluid mobile at all. And also, since quartz forms at such low temperatures in an igneous context, relatively considered, like it's the last to crystallize. And you can also, if you melt a rock, you can get quartz from that. Like quartz is if you melt a rock at a very low temperature, you take the magma and then that magma gets cooled. That will have a lot of quartz in it, but not a lot in the way of mafic minerals like olivine or pyroxene. Quartz is pretty darn stable at Earth's surface, and so it's often the last mineral left. Now, another example of chemical weathering that's pretty interesting is hydration, which is something that happens with clays. And that's actually something we take advantage of with kitty litter. Because what happens is that when some minerals take water up, they'll expand. And the water will actually they'll absorb the water into their chemical structure. They'll go from being one type of mineral that doesn't have water incorporated into it into a new type of mineral that does have water incorporated into its chemical structure. And I didn't really go over it, but some minerals actually are said to be hydrated. They have H2O molecules bonded to the metal ions in the mineral. And in some cases, those form as a result of chemical weathering. When rainwater reacts with minerals and those minerals take the water up and get hydrated. Another really good example of chemical weathering is oxidation, or what you all might know as rust, or what I generally know better as rust. And rust is one form of chemical weathering that happens when iron gets exposed to oxygen for too long, or to water, because the water has oxygen molecules in it that will cause the same reaction. So water is actually reacting with iron to make a new mineral. It's reacting with if you leave a sheet of iron out, especially if it's in a rainy area, either the oxygen in the air or the oxygen in the water molecules in falling rain or whatever will actually react with the iron to oxidize it and create a completely new mineral. And that mineral is hematite, or simply rust. Hematite is simply the mineral name for rust. And likewise, if you see other rocks that look stained, it's often because the minerals in them are oxidizing because they've been exposed to air or water. So in this picture with the penny, pennies aren't completely made of copper, but this is kind of what copper looks like when it's not oxidized. And copper will actually form it'll form blue or greenish minerals when it gets oxidized. That's why copper mines, you often find really beautiful turquoise minerals like turquoise or chrysocolla or azurite and malachite, because those are all different types of copper oxides. So, and often the way this manifests is that the surface of the rock will appear kind of stained from the oxidation. And when you're studying these rocks, you have to be careful that you aren't studying the part of the rock that's been oxidized. If you're going to do chemical work on these rocks, you have to you have to kind of cut off the parts that have been oxidized and carefully remove those parts so that you're left with a part of the rock that isn't affected by chemical weathering. Because if you're trying to study the chemistry of the rock, you don't want to study the part that's been affected by water. Now, one example of a type of physical weathering actually that's really cool is ice wedging. And the way that essentially any physical weathering works is that it'll speed up as the surface is broken down and as you get the rock made into smaller pieces and more surface area is exposed. More cracks will provide much more surface area to be attacked either by chemical or physical processes. And when ice wedging occurs, what happens is that water actually expands when it freezes, which you've discovered if you've ever accidentally filled a water bottle all the way up and then put it in the freezer without leaving space. The ice can actually break a water bottle if you do that, and it can actually break rocks too. You get little cracks full of liquid water, and then when that liquid water freezes, the force of the expansion actually pushes the rock apart and can cause it to crack. And in this particular case, in this picture here, now not only is the outside of this boulder exposed for further weathering, there's a crack on the inside that air and water can now access. And this speeds up the process. You can also have physical weathering from a number of things. Another type of physical weathering that's pretty common in desert areas is thermal expansion. And this often occurs in deserts where you have really big differences between nighttime and daytime temperatures, because that will actually cause the minerals in the rock to expand and contract, not very noticeably to us, but just enough that it can cause the minerals to kind of pop out from where they're embedded in the rock already. And this is the same way that metal will do this. Bridges are actually built with this interlocking mechanism so that, especially in areas with extreme temperature changes, so that the bridge you don't simply have a solid piece that's going to be forced apart by thermal expansion. It's built with an interlocking mechanism so that it'll still be held together, even if the metal expands just a bit. And rocks don't have any feature like this, of course. Rocks simply often will fall apart from this. And if you ever get the chance to go to the Owens Valley, there's a place called the Alabama Hills where you have these really beautiful stacks of granite, kind of these they look kind of like silos of granite almost. And these granites have what are known as phenocrysts. They have larger crystals of orthoclase feldspar, or the pink feldspar. And what'll happen, because this area undergoes so much thermal expansion, or because there's so much in the way of temperature changes, is that the crystals of orthoclase feldspar will sort of pop out. They'll just kind of pop out like rubble. And you can just walk up to the granites and just pop them out with your hands, because they've been so destabilized. Thermal expansion has caused them to be kind of falling out from the rock. You also have another example, and I actually just noticed these dinosaurs on this example, which is kind of funny, because that's not something you don't really have a lot of dinosaurs in California. But one type of physical weathering can occur when you have granites or other igneous rocks that originally formed intrusively. When those rocks get exposed to the surface from erosion and uplift, those rocks formed under relatively warm conditions and also under higher pressures. And you would think that the pressure dropping wouldn't necessarily hurt it, but if you've been on an airplane, if you've been in any situation, or if you've gone up a mountain really fast and the pressure changes, whether it's the pressure getting bigger or smaller, that causes your ears to hurt. Pressure changes in general will cause your ears to hurt, and they will cause strain on the rocks. And what happens when those rocks are exposed at the surface is that the pressure drops relatively rapidly from their perspective, and that causes them to form cracks. That causes jointing. And this is something we see a lot in granites in places like the Sierra Nevada, where the overlying extrusive rocks, or the rocks formed as part of the volcanoes, are all gone. And now the intrusive plutons, the granites underlying them, are being uplifted. And that's actually, on a side note, how Arches National Park formed and how frequently arches form. They form from a combination of jointing and ice wedging, where you have these rocks that have been buried they get broken into these little fins by ice wedging, and they experience a release of pressure that causes them to start breaking off, and over time it will form into these arch shapes. And the arches don't last forever either. Those fall down eventually as a result of this, but as long as you have some arches, you'll still get people coming to the park. So I have just a few more slides. Does anybody have questions up until this point? Cool. So I'll talk a little bit about different agents of weathering now. So living things like tree roots can actually be really effective weathering agents, both in a physical and chemical sense, because not only do the roots take advantage of cracks or other weak points in the rock to force the rocks apart, which leaves more surface area and then leaves them more at risk for further weathering, they also produce chemical enzymes, and those enzymes actually chemically alter the rocks and break them down chemically. And over time, the combination of physical and chemical weathering turns the rocks into soil. And it's not just trees doing this, smaller plants do this as well. Lichens, when lichens are growing on rock, like when you have those little, they're not quite plants, they're really more of a fungus, but lichens are weird. I'm not going to go into what they are really, but when you see lichens growing on rocks, they are actually physically and chemically breaking down the rock. They're creating spaces in the rock and also producing enzymes that break the rock down for nutrients that they can access. And often lichens are the first plants to show up in an area that's, say, where you have a volcano erupting in the ocean and producing a new island, or if you have an area that's been covered by glaciers that gets exposed pretty rapidly. And one reason, in fact, when I was in Antarctica and studying the rocks there, if you've looked at any of the pictures I've showed you from my Antarctica trip, it was in an area that doesn't have a lot of glaciers covering it. And Antarctica doesn't really have much alive in the interior at all. You have very little growing there. You don't have live penguins and seals living there. It's just kind of a desolate wasteland. And from a geology perspective, that's actually a good thing because it means the rocks have not been broken down very much by biological activity, and they're still pretty intact. And also, you can kind of think about what humans do as a form of biological weathering, because we've done things like make Mount Rushmore, or we've carved out large areas for pit mining. And again, it's a good example of how weathering can be. You can kind of think weathering can be any process that removes material. And humans play a relatively small part in weathering, relatively small compared to the grand scale of the processes that break rocks down, but important in the fact that pit mining can leave a pretty big impact. In this case, what we'd consider to be kind of a scar left on the land. Now, another agent that can cause weathering is wind. And a lot of the time, the agent that transports and weathers is water, but wind can also carry sand-sized particles and smaller particles than that. And it'll just whip up everything and transport it to wherever the wind falls. And this is common in deserts where you don't have a lot of plant growth, where you don't have a lot of plants holding the soil and sediment down. And this can cause sandstorms to lift up and transport large amounts of sediment. And this is one reason why deforestation is so devastating, because when the plants are there, that actually does a pretty good job of holding down the sand and the soil and whatever else is in the ground in place. But if you take the trees away, then the wind can much more easily just rip all that up. And another good example of that is actually the Dust Bowl in the United States, when poor agricultural practices led to the soils becoming very not supportive of crops anymore. So the harder it was to grow crops, the more that you simply had dust blowing around because there weren't plants holding the soil down anymore. And glaciers can also weather. Glaciers, in Antarctica, glaciers do a lot of the weathering because you don't have much liquid water. And they tend to be very effective at removing material. They basically bulldoze everything out of their path. They grind up the rock underneath them. Sometimes they pluck little bits of rock with them. And they just sort of push everything to the front. And that's why you see these piles of sediment at the ends of glaciers, often in pictures, these things known as terminal moraine. And glacial deposits tend to be really poorly sorted. They tend to be sediments of all different sizes simply because the glaciers push everything out of their way. So just a couple more slides. Does anybody have questions about any of the stuff I've gone over so far before I go over some of the minerals that you might see in the lab that we're going to do today? Cool. So I do want to address some of the minerals. And one of those minerals that we've seen a couple times in this presentation is halite, or rock salt, or sodium chloride, which largely forms from the sodium that is chemically eroded from feldspars. And some ways you can identify it are that it has very well-formed cubic cleavage. It breaks off into cubes. It breaks off into pieces that have nice, smooth cleavage surfaces on the top and bottom, on this side and on this side. And you can also identify halite by the fact that it tastes salty. Obviously, in this online lab, that's not something you're going to be doing. And that's not something I ever make people do, because putting your mouth on samples that other people might have done so on is kind of questionable safety value. A second mineral is gypsum, which forms, which is a very, very soft mineral, and it looks kind of like halite, but it doesn't taste salty because it's actually formed from sulfate instead. It also has different cleavage. It tends to have one really good direction of cleavage, so it's kind of platy and flakes off, kind of like a mica. Technically, it has two planes of cleavage, but one of them doesn't manifest very clearly. So it's easy to think of it as a sort of sheet-like or platy mineral. And it also forms as an evaporite. It forms where lakes have dried up and left behind minerals. Now, quartz doesn't form as an evaporite, and we've talked about quartz before in an igneous context. Quartz forms as part of igneous rocks often. And again, it's common in sedimentary rocks because it is so resistant to weathering. The sediments weathered from igneous rocks will usually have some quartz, especially if we're talking about the granites, the sediments eroded from the granites that we have on land, which are felsic or light colored and have a lot of quartz in them. And in general, the more quartz and the less of other minerals you have, the more heavily weathered the sediment is. And that's a term that people refer to as maturity, sediment maturity. Calcite, meanwhile, can form as an evaporite, but something that's really cool is that it can form in the shells of living organisms. Calcite is actually what makes up corals and snail shells, and also the little shells of plankton, even, of little phytoplankton in the ocean. And again, calcite sometimes forms as an evaporite, but if it doesn't form as an evaporite, what'll happen is that these animals or plants that have extracted and made calcite will die, but the calcite is hard, so it'll be left behind, and it'll collect and over time form limestone. And actually, one cool thing about limestone, the rock formed from calcite, is that sometimes you can see fossils in them because those fossils are actually the calcite itself. And it's distinguished by, it has 3 planes of cleavage, but it doesn't have, they don't meet at 90-degree angles. Calcite doesn't form boxes, it forms kind of these rhombus shapes. And it also reacts with acid. Meanwhile, this is a really nice sample of muscovite mica. And you'll notice there's these little sheets that are kind of forming together. And muscovite mica also forms in igneous rocks frequently. And it breaks down relatively easily, especially compared to quartz. So if it's present, that often indicates that the sediment hasn't been very heavily worn down. Likewise, we also often find feldspars, and feldspars do a little better than mica does. Feldspars, if feldspars are present in significant amounts, that means that you're sort of intermediate. Like if there's not much, if there's quartz, if there's a decent number of feldspars and then not very many micas and not very many mafic minerals, that is sediment that has undergone some chemical weathering, but not a lot. Not a lot in that there's still some feldspar there. Often you'll look at sediment and sand and you'll see little pink fragments, and those pink fragments are actually from the orthoclase feldspar that we've seen in lab. Okay, so today's lab basically has 4 types of questions. The first few questions have you look at some of the igneous rocks that you've seen before, and Maki, get away from the computer. And you look at some of the rocks to identify whether they're fine-grained or coarse-grained, or whether they're mafic or felsic. And then we have you look at some sand samples, because sand is a type of sediment that is defined by how big the pieces are in general. Sand can be broken down from any different rock. If you think about how Hawaii has its famous black sand beaches, it's sand because it's sand-sized particles, but it's not going to look the same as the beaches that you have in Mississippi or Florida, because those are sands that are almost entirely made of quartz. Whereas the black sand beaches in Hawaii form where you have volcanic rocks nearby breaking down and ending up very close to, and volcanic rocks that aren't very far from the ocean, they get broken down and there's not much time to chemically weather them, so they still have a lot of mafic minerals in them. But you'll be looking at a couple pictures of sand samples to look at what type of minerals you can see and what type of rock they might have come from. And there's a couple of examples then where you'll be asked to figure out whether you think something underwent physical weathering or chemical weathering, or both, whether you see evidence of both. And then finally, you'll be identifying some of the sedimentary minerals, and there is a flowchart linked in the Canvas exercise to help you do that. Most of these minerals, if not all of them, are ones that you've seen before. And there's also a chapter from the Introduction to Geology book linked on Canvas that's a good reference for this lab. So that's all I have for the presentation. Does anyone have questions? All right, then, I will leave the lab open for you, and I will be around to answer questions. And Let me know if you need me to explain anything in the lab itself as you're going through it. I'm happy to work through it. All right, I'll be ending the recording in just a sec, and once I stop the screen share, I'll be uploading these slides to Canvas also, so you can take a look at them there.